Hi friends, welcome to the lecture of linear algebra. Today we are going to study one important theorem which is on the diagonalization of a linear operator, and which is the last point of our diagonalization and triangulation of a linear operator. Okay, now which is a theorem. Okay, let V be a finite dimensional vector space vector space over the field here and TB a linear operator on V. Then T is diagonalizable diagonalizable if and only the minimal polynomial for T has the form has the form that is minimal polynomial for linear operator T is nothing but x minus c1 into x minus c2 up to so on x minus ck, where c1 c2 ck, where c1 comma c2 to so on ck are distinct elements of field F, distinct elements of field F or distinct characteristic values of T. Distinct characteristic values of linear operator. Okay, so here we have given that T be a linear operator which is defined on a finite dimensional vector space V over the field F, and then we have to prove that the linear operator T is a diagonalizable operator if and only if the minimal polynomial for the linear operator T has the form that is P of x can be written as, that is P of x is nothing but the minimal polynomial, and which can be written as x minus c1 into x minus c2 up to so on x minus ck, where c1 c2 up to so on ck are the distinct characteristic values of the linear operator T. So in first step, let what should be we have given that T be a linear operator on finite dimensional. Let us suppose V be a n dimensional vector space. As it is given that it is a finite dimensional, let us suppose that its dimension will be n. Let T be a linear operator on n dimensional vector space. N dimensional vector space V over field F. Now, in first step, let us suppose that T is a diagonalizable operator and prove that the minimal polynomial for the linear operator T has a this form. And in second step, we have to prove that the minimal polynomial for T can be expressed in this form. Then we have to prove that T is a diagonalizable operator. Let us suppose that, assume that T is diagonalizable. As T is diagonalizable, then by definition, there exists an ordered basis. Curly B for vector space V such that the matrix A of linear operator T with respect to ordered basis curly B is a diagonal matrix, which is from definition of diagonalizable operator. Okay, so here we get a matrix A which is a diagonal matrix with respect to the ordered basis curly B. Let us suppose that A is nothing but matrix of linear operator T with respect to ordered basis B, and which is nothing but a diagonal matrix C1 I1 0 up to so on 0 C2 I2 and so on 0, 0, 0, and up to so on Ck into Ik. And V is a vector space of dimension n, then A is a matrix of order n cross n, where C1, C2, up to so on Ck are characteristic values of linear operator T, and each Ci is repeated di times. Okay, repeated di times, and Ij is a dj cross dj identity matrix. This is from our given statement, that is T is a diagonalizable operator. As T is a diagonalizable operator, then there is a matrix A of a linear operator T with respect to order basis B such that which is a diagonal matrix, and this one is the matrix A which is the diagonal matrix where C1, C2 up to so on Ck are the distinct characteristic values of the linear operator T, where each characteristic value Ci is repeated di times, and with the corresponding Ij are the dj cross dj square matrices. Okay, now we know that the characteristic polynomial of T is given by, in last lecture we have seen how to find out the characteristic polynomial of a linear operator, that is f of x equal to determinant of xi minus i, which is nothing but f of x is nothing but x minus c1 to the power d1 into x minus c2 to the power d2 up to so on x minus ck to the power dk, which is the characteristic polynomial of a linear operator T. Now claim that P of x equal to x minus c1, x minus c2 up to so on x minus ck is the minimal polynomial. That is we have to do. Okay, already we know what is the its characteristic polynomial, and we have to prove that this polynomial P of x equal to x minus c1 into x minus c2 into up to so on x minus ck is a minimal polynomial for the linear operator T. And any polynomial is said to be minimal polynomial for a given linear operator T if it is a monic polynomial of lowest degree which annihilates the linear operator T. Now, by its nature itself, it says that it proves that the given polynomial P of x is a monic polynomial. Since here coefficient of each x, which is a variable, has 1. So if we take multiplication, then the highest coefficient of highest term is obviously 1. Therefore, this given polynomial is a monic polynomial. Therefore, here already P of x is a monic polynomial. So now it remains to prove that this polynomial is a lowest degree polynomial which annihilates the linear operator T. That is, here we have to prove that P of T is equal to 0. Okay, and P of x is the lowest degree polynomial which annihilates the linear operator T. Okay, now let alpha be a characteristic vector corresponding to characteristic value C, to characteristic value Cj. Then by definition we get T of alpha is equal to Cj of alpha, which is from the definition of characteristic vector, and which is nothing but t minus cj into I of alpha is equal to 0 for any alpha which is a characteristic vector corresponding to characteristic value cj. Okay, now put x equal to t in this equation. Let us take this equation as 1, that is characteristic polynomial as a 1 and this one as a 2. Now put x equal to t in 2. Put x equal to t in 2. We get p of t is nothing but t minus c1, t minus c2 up to so on, t minus c2. Now operate this p of t on vector alpha. Then we get which implies p of alpha is equal to, let us write this c1 as c2 up to so on ck as c1 into I, that is t minus c1 into I of alpha plus t minus c2I of alpha plus up to so on t minus cky of alpha. But we know that t minus cji of alpha is equal to 0 for any characteristic polynomial cj of a linear operator t. Then this product must be equal to 0, since t minus c1 I of alpha will be equal to 0. T minus c2 I of alpha is again 0. Up to so on t minus ck I of alpha is also 0. Therefore, which is 0. So which implies p of alpha is equal to 0. Okay. Now from this we conclude that now we have to prove that this p of alpha is equal to 0 for any alpha belonging to vector space V. Here, given that t is a diagonalizable operator, as t is a diagonalizable operator, then by definition of diagonalizable operator, there exists a basis curly B for V, such that each vector of this curly B, that is the basis B, is a characteristic vector. As each vector of basis is a characteristic vector, then V is a vector space which is spanned by the characteristic vectors. Here, V is a vector space spanned by characteristic vectors. Okay. So here we take any arbitrary alpha which is a characteristic vector of a linear characteristic vector corresponding to characteristic value Cj of a linear operator T. Now each vector of this V is a characteristic vector. Then P of beta equal to 0 for all beta belonging to V. So P of beta will be equal to 0 for all beta belonging to V. From this we conclude that P of x annihilates linear operator T. Now we know that there is one theorem. The roots of characteristic polynomial and minimal polynomial for a linear operator are same except the multiplicity. As here P of x contains every root of characteristic polynomial. So from this we conclude that there is no polynomial other than this P of x which have degree less than P of x and which annihilates the linear operator T. Since if we have to take a minimal polynomial, then there is one basic condition that every root of a characteristic polynomial is also a root of this minimal polynomial P of x, and from the given this minimal polynomial P of x, there is no possibility that there is any other minimal polynomial which have degree less than this P of x. Therefore, this P of x is only the lowest degree polynomial which annihilates the linear operator T and which is a monic polynomial. Then by the definition of minimal polynomial, this P of x is the minimal polynomial, which implies P of x is a minimal polynomial and which is the required result. Okay. So here we have in first step we have taken T is a diagonalizable operator and we have proved the minimal polynomial for the linear operator T has this form, that is P of x equal to x minus c1 into x minus c2 into up to so on x minus ck is nothing but the minimal polynomial for a linear operator T. Now we have to prove the converse part. Okay. Conversely, let P of x equal to x minus c1 into x minus c2 and up to so on x minus c2 is a minimal polynomial for linear operator T where c1, c2, up to so on ck are distinct characteristic values of linear operator T. Now we have to prove that T is diagonalizable. Okay, that is we have to prove that there exists a ordered basis curly B for a vector space V such that each vector of this basis is a characteristic vector. Now let W be a subspace spanned by characteristic vectors spanned by all the characteristic vectors spanned by all the characteristic vectors of a linear operator T. Okay, now here we have taken one subspace W which is spanned by all the characteristic vectors of a linear operator T, and we have to prove that there is one basis curly B for V for vector space V such that each vector of this curly B is a characteristic vector. Now if we have to prove that this T is a diagonalizable operator, then we have to prove that this W is nothing but the vector space V. Since W is spanned by all the characteristic vectors of a linear operator T. If we prove that W equal to V, then from the definition of diagonalizable operator, T must be a diagonalizable operator. Then we have to claim this W is equal to, if we prove W equal to V, then V is a vector space which is spanned by all the characteristic vectors of a linear operator T, and then from the definition of diagonalizable operator, T must be a diagonalizable. Okay, now we have to claim that W will be equal to V. So if possible, suppose that W is not equal to V. As W is not equal to V, then W must be a proper subspace of V, and dimension of W is equal to K. As dimension of W is K, then curly B equal to alpha 1, alpha 2 up to so on alpha K is an ordered basis for W. Since the dimension of W is K. Okay, and W is a subspace which is spanned by all the characteristic vectors of a linear operator T. Then the basis set of this W is a collection of characteristic vectors. Then by the definition of characteristic vector, T of alpha I is equal to Ci of alpha I whenever I is running from 1 to T, which is from the definition of characteristic vectors, and W is a subspace which is spanned by all the characteristic vectors of a linear operator T. Now here, as dimension of W is not equal to dimension of V, then dimension of W is less than the dimension of V. Therefore, W is a proper subspace of V. Now here, as T of alpha I is equal to Ci into alpha I, then this W is a invariant under T. So if we take any element belonging to W, then its T image is again in W, since it is a linear combination of elements of this basis, and its linear combination is again in W. Therefore, T is invariant under that. Sorry, W is invariant under T. Here, W is invariant under T. Any operator T is any subspace W of a vector space V is said to be invariant under T. If we take any alpha belonging to W, then its T image is again in W. As here, T of alpha I is equal to Ci of alpha I. Then if we take any element in W, then its T image is again in W. Therefore, from this we conclude that W is invariant under linear operator T. So here W is a proper subspace of V which is invariant under T, since W is not equal to V. Here W is proper subspace of vector space V which is invariant under linear operator T. Okay, which is invariant under T. Again, in previous lectures we proved one theorem which is if T be a linear operator which is defined on a finite dimensional vector space V such that the minimal polynomial for T has a linear factors, that is P of x can be expressed as x minus c1 into x minus c2 into up to so on x minus ck, and if W is any proper subspace of V which is invariant under T, then there exists one vector alpha belonging to V such that alpha is not belonging to W but T minus Ci of alpha is belonging to W. So here T be a linear operator which is defined on a finite dimensional vector space V, and P of x equal to x minus c1 into up to x minus c1 into x minus c2 into up to so on x minus ck is a minimal polynomial for the linear operator T, and W is a proper subspace of vector space V which is invariant under T. Then from that theorem there exists a vector alpha belonging to V such that alpha is not in W and T minus Cji of alpha is belonging to W for some characteristic value Cj, Cj of linear operator T. Okay, now let beta is nothing but T minus Cji of alpha. Here we have taken T minus Cji of alpha is nothing but beta, and T minus Cji of alpha is belonging to W, which implies beta is belonging to W. As beta is belonging to W and curly B is a basis for W, then this beta can be expressed as a linear combination of elements of its basis set, which implies beta can be expressed as A1 alpha 1 plus A2 alpha 2 plus up to so on AK alpha 2. Okay. Now, where A1, A2 up to so on AK are K scalars, where A1, A2 up to so on AK are scalars. Okay. So here we have taken for particular beta. If suppose any beta I is belonging to W, then this beta I can be expressed as a linear combination of elements of basis sets of W, that is alpha 1, alpha 2 up to so on alpha k. Therefore, for any beta I belonging to W, this beta I can be expressed as linear combination of elements of basis set of W, where I is running from 1 to. Again, here we know that each alpha is a characteristic vector of a linear characteristic vector belonging to basis set of W. Now, here we know that if alpha I is a characteristic vector corresponding to characteristic value Ci, then Ai into alpha I is also a characteristic vector corresponding to same characteristic value Ci. We have already seen this. Since any linear combination of characteristic vector is again a characteristic vector, therefore if alpha I is a characteristic vector corresponding to characteristic value Ci, then its linear combination is also a characteristic vector corresponding to the same characteristics value Ci, which implies beta I is a characteristic vector corresponding to characteristic value Ci. Okay, which implies T of beta I is equal to Ci into beta. Therefore, here as beta is belonging to W, then any beta can be expressed as a linear combination of elements of its basis set. That is, here beta can be expressed as beta 1 plus beta 2 plus up to so on plus beta 3. Okay, now let h of x belonging to ring of polynomial fx be any polynomial. Okay. Now, again we know that one theorem, that is if T be a linear operator on a finite dimensional vector space V and h of x be any polynomial over the field F and C be any characteristic value of a linear operator T, then h of T of alpha is nothing but h of C, hc into alpha. Which is from, we have already proved this theorem, that is if T be a linear operator on a finite dimensional vector space V and h of x be any polynomial over the field F and C be any characteristic value of a linear operator T, then ht of alpha is nothing but h of C of alpha. So, okay, now operate this h of t on your beta. That is beta 1 plus beta 2 up to so on beta k. Therefore, from this h of t of beta is nothing but h of t of beta is nothing but h of t of beta 1 plus beta 2 plus up to so on beta k. As h of t is a linear, which implies which is nothing but h of t of beta 1 plus h of t of beta 2 up to so on h of t of beta k. Okay, again from this theorem. This is for particular value c. Therefore, h of t of alpha is nothing but h of c of alpha. Okay, therefore, here we get there are k characteristic values corresponding to this beta 1, beta 2 up to so on beta k. Therefore, which is nothing but h of c1 of beta 1 into beta 1 plus h of c2 into beta 2 plus up to so on h of ck into beta k, where this h of c, hc1, hc2 up to so on hck are the scalars. Now they are the scalars and beta 1, beta 2 up to so on beta k are the members of W. Therefore, as W is a subspace, then it is closed under the linear combination of this beta 1, beta 2 up to so on beta k. As hc1, hc2 up to so on hck are scalars, then they are again belonging to W. Therefore, this is belonging to W. Since beta 1, beta 2 up to so on beta k belonging to W and W is a subspace. Okay, so which implies ht of beta is belonging to subspace W for any polynomial h of x belonging to x. Okay. Now, here we know that the p of x equal to x minus c1 into x minus c1 into x minus c2 into up to so on x minus ck is a minimal polynomial for a linear operator t. Therefore, the minimal polynomial px can be written as that is Px can be written as x minus cj into q of x. Okay. Cj is one particular root belonging to this c1, c2 up to so on ck. Then p of x can be written as x minus cj into q of x whenever and q of cj is not equal to 0. Since cj is not equal to 0, cj is a one distinct root belonging to this one among the c1, c2 up to so on ck, and this one is the particular polynomial for that. Therefore, there is no characteristic value belonging to this q of x. Therefore, q of cj is not equal to 0. Okay. Now define. Let us define one function. Define k of x is nothing but h of x minus C. Sorry, Q of x minus QCJ.
Qx minus Q
CJ. Okay. Now, here as CJ is a root of polynomial CJ is a root of minimal polynomial, then K of CJ is nothing but Q of CJ minus Q of CJ, and which is equal to 0. Therefore, CJ is a root of K of x, which implies CJ is root of Kx. Okay, therefore, this K of x can be written as Cj is the root of K of x, then K of x can be written as x minus Cj into something g of x. Since Cj is the root of K of x, therefore K of x can be written as x minus Cj into g of x. But K of x is nothing but Q of x minus Q of Cj, and which is nothing but gx into x minus Cj. Okay, now put x equal to t in this equation. Then we get put x equal to t, which implies q of t minus q of Cji equal to g of t into t minus Cj of I. Now operate this one alpha. Then we get q of t of alpha minus q Cj I of alpha is equal to g of t into t minus Cj I of alpha. Okay, which is nothing but q of t of alpha minus q Cj I of alpha is equal to g of t. But in previous we have taken t minus Cj of alpha is nothing but beta. Okay, which is beta. Now here we have proved that if h of x is any polynomial over the field here and beta is belonging to w, then h of t of beta is belonging to w. Therefore, as here beta is belonging to w and g of x is any polynomial over the field here, that q of x can be written as x minus cj into g of x for some g of x belonging to fx. And from this one, if h of x is any polynomial over the field here, then and beta is belonging to w, then h of t of beta is belonging to w, which implies g of t of beta is also belonging to w, since beta is belonging to w, and g of x is any polynomial over the field here, which implies this one is belonging to w. If g of t of beta is belonging to w, as left hand side is belonging to w, then this must be belonging to w, which implies q of t minus q of t of alpha minus q Cj I of alpha is belonging to subspace w. Let us take this one as a star. Okay. Now we know that minimal polynomial can be written as the minimal polynomial is nothing but p of x into x minus cj into q of x. Now, if we put x equal to t, then minimal polynomial becomes the minimal polynomial becomes p of t, the minimal polynomial. Okay, the minimal polynomial becomes p of t is equal to t minus cj I of into q of t. Now operate this on alpha. P of t of alpha is equal to t minus cji into q of t of alpha. Now p of t of alpha is equal to t minus cji. Let us take this one as a gamma, where gamma is equal to q of t of alpha. Okay. Now again, as p is a minimal polynomial for a linear operator t, then p of x annihilates the linear operator t, then its value becomes 0. Since p of x is a minimal polynomial, as px is a minimal polynomial, then it annihilates the linear operator t, which implies which is equal to 0 into t minus cji of gamma, and which is nothing but t of gamma minus cji of minus
Cji of gamma is equal to 0, which implies Q of gamma is equal to Cj of gamma.
Now, if gamma is not equal to 0, if gamma is not equal to 0, then by the definition of characteristic vector, this gamma is a characteristic vector corresponding to characteristic value Cj. That is, if gamma is not equal to 0, then gamma is a characteristic vector corresponding to characteristic value Cj. Okay, now if gamma is non-zero, then gamma is a characteristic vector corresponding to characteristic value Cj. As gamma is a characteristic vector, then it is belonging to W. Since W is a vector subspace which is spanned by all the characteristic vectors of a linear operator T. As here gamma is a characteristic vector, then it must be belonging to W. So gamma is belonging to W. As gamma is belonging to W, which implies gamma is nothing but Q of T of alpha, which implies Q of T of alpha is belonging to W. It is possible when gamma is not equal to 0. Then there is only possibility that if gamma equal to 0. If gamma equal to 0, if gamma is equal to 0, which implies Q of T of alpha is equal to 0. As Q of T of alpha equal to 0 and W is a subspace which is spanned by all the characteristic vectors of a linear operator T, therefore 0 is also a member of W, which implies Q of T of alpha is again belonging to W. Therefore, for both gamma equal to 0 and gamma is not equal to 0, gamma is a member of W. Okay. Now, here Q of T of alpha is belonging to W. Let us take this one as a star. Now, from star 1 and star 2, Q of T of alpha minus Q Cj of alpha is belonging to W and Q of T of alpha is belonging to W. Then any linear combination of these two is again belonging to W, which implies Q of T of alpha minus Q Cj I of alpha Qci of alpha is minus this one Q of T of alpha is belonging to W, which is from star 1 and star 2. Okay. Now, which implies Q of T of alpha is cancelled, which implies Q minus Cji of alpha is belonging to W. Now here alpha is not belonging to W. Here alpha is not belonging to W. Since we know that alpha is any characteristic vector of a linear operator T, that is alpha is belonging to vector space V such that alpha is not in W and T minus Cj of alpha is belonging to W. So alpha is not belonging to W. Then there is only possibility that this Q of Cj will be equal to 0, which implies Q of Cj is equal to 0. If possible, suppose that if Q of Cj is not equal to 0, Q of Cj is not equal to 0, and here already Q of Cj of alpha is belonging to W, which implies 1 upon Q of Cj. Q of Cj is not equal to 0, then it can be written as 1 upon Q of Cj into Q of Cj minus Q of Cj of alpha is equal to Q of Cj is constant, cancel, and here we get alpha, which is belonging to W. Okay. If Q of Cj is not equal to 0, then this can be written, Q of Cj of alpha can be written as 1 upon Q of Cj into minus of Q of Cj of alpha. Q of Cj cancel, and alpha, which is alpha is belonging to W. As alpha is belonging to W, then we get a contradiction to alpha is not belonging to W. So here Q of Cj is not equal to 0 is not possible. If Q of Cj is not equal to 0, then alpha is belonging to W. So Q of Cj must be equal to 0, which implies Q of Cj is equal to 0. But which is again a contradiction. Since for minimal polynomial, we can write as P of x is nothing but x minus Cj into Q of x, where Q of Cj is not equal to 0. But here Q of Cj is equal to 0, therefore which is contradiction. And this contradiction arises due to our wrong assumption, that is W is not equal to V. That is, we have considered, if possible we have supposed that W is a proper subspace of V. And from this wrong supposition, we get Q of Cj is equal to 0. Hence, our supposition is wrong. So, W is not equal to V. W not equal to V is not possible. As W is not equal to V is not possible, which implies W must be equal to V. That is, W and V are the same vector spaces. And we have considered that W is a vector space which is spanned by all the characteristic vectors of a linear operator T. As W is equal to V, which implies V is vector space spanned by all the characteristic vectors of linear operator T. As V is a vector space which is spanned by all the characteristic vectors of a linear operator T, then from the definition of diagonalizable operator T is a diagonalizable operator. T is diagonalizable. As V is a vector space which is spanned by all the characteristic vectors of a linear operator T, then basis set of vector space V contains all the characteristic vectors of T, and which is the definition of diagonalizable operator. Okay, thank you for watching the lecture.